So the topic of today's seminar is, it will be not so much about ATENA, although I will of course show some ATENA screens because we of course always like to show our software. But I will more focus on some general topics like how to apply nonlinear analysis in practical situations, in practical projects, where basically we always have to introduce some safety framework. So main focus of this presentation will be on the safety formats for nonlinear analysis. Then in the next part, I will show this on two practical cases, because in nonlinear analysis, it is of course not just the problem of selecting a safety format, but also, let's say, to formulating your problem and how to address it. So on two examples, I will show some typical ways how this can be done. And maybe just if there is time, I will also show some recent new features in the latest version of ATENA software. So let me share my screen now. And I will start the presentation. And as I told you, the first one is about this topic of global safety formats. So what I will be talking about? I will talk about the safety formats, and then also I'll spend some time on quantifying the uncertainty in the model. And most of the topic will be focused on ULS. That means the ultimate limit state for the ultimate limit state. But also I will briefly mention the service limit state, mainly the crack width. So I will just, to demonstrate the topic, I want to show some example very briefly. So for instance, this is a project in India where recently they constructed this large campus. Sorry, I see I have the automated presentation on. Switch it off. Okay. It's working now. So we participate in a small consulting projects. The topic there was to check this structure element, which was a floor slab on top of this building, where the way I understand it, that's where the management was supposed to sit and look over the campus. So this was a very thick slab with some steel elements attached to very thick concrete slab. So we of course develop a finite element model. We apply the load combination that we need to check, and in nonlinear analysis we typically do so-called global assessment. That means we keep increasing the load until failure, and then this is the typical results that we obtain. So we have kind of a load displacement curve where we keep increasing the load, monitor some largest deflection, and at some point we have a failure of our structure, virtual failure, that means failure of our model. And of course the question is, then we can compare it with the design load level, which is this thick solid green line. And then the question is, what should be the safety margin? That's maybe the topic of the today presentation. We are using finite element analysis. This is just to describe slightly the method. That means our structure is divided into finite elements. Inside each finite element, we have integration points. And at this integration point, we are always calculating the strains from the geometric equations and then the stress from a constitutive equation. So this is the main part actually where our software ATENA comes to play, where we introduce our nonlinear material models, introducing the cracking and so on. So that's the main focus of ATENA software. And how the analysis goes is that we move along this kind of virtual load displacement curve, always by an elastic predictor. And then once we check the stresses, introduce our constitutive model, we have basically a corrector to the step 2. So the analysis always goes step by step by increasing the load. And always there is this predictor phase where we assume elastic response. Once we check the stresses, we correct the internal forces in the structure, which usually means a drop, to come back to the load displacement curve corresponding to nonlinear behavior. Brief summary of the material models that we are using. So if you think about a uniaxial law, we have a very brittle behavior in tension. In compression, our concrete material first is elastic. At some point, it starts to be nonlinear up to the compressive strength. And then when the compressive strength is reached, we reach a softening regime in compression. Both softening in compression and softening in tension in ATENA is controlled by the crack band model, which takes care of the proper dissipation of energy in these damage processes. If we now look how this material model behaves in 2D case, we can see this kind of failure envelope. And in 3D, we are using full three-dimensional failure surface. We are using the Menetre-Willems 3-parametric surface, which looks like this kind of cone with triangular shape with rounded corners. I told you that we are using this crack band approach. So the basic idea of this approach is that we assume that there is a single crack inside our finite element, but the behavior of this crack is smeared over the volume of the element. And this smearing is done through this crack band size, LT. And that means the crack opening is basically a multiplication of fracturing strain times this crack band size. Well, what does this mean in finite element analysis? So this means that as the structure is loaded and the cracking develops, we see a localization of the cracking into a band of finite elements. So that's why this approach is called the crack band model. So now let's look at, also open the chat window so that I can see if there are any questions. Okay, now let's talk about this limit state verification by this global approach. So let's see how it compares to the classical approach which we typically use in design of reinforced concrete structures nowadays. So what we do is we have a structure. This is this figure on the left top. We apply some loads on it, some load combination corresponding to design load combinations that we have to verify. And then we typically check the most critical sections. And in these most critical sections, we are checking this kind of equations that the design load, which in this case is typically the internal forces, that means moments, shear force, normal force at these critical sections, whether they are smaller than RD. In this case, it means the design strength of the particular investigated section. Now, when we go to nonlinear analysis, we apply our loads and we keep increasing those loads up to failure. And then we check whether this failure load that we calculate is RGD, global design, we can say it's a global strength of our structure. should be bigger, of course, than the design loads, FGD. Now we already introduced a small problem. We are talking here about an equation where we have two numbers, but in reality, when we are investigating a real structure, it is typically not a single number because we have a load combination, which often includes surface loads, sometimes point loads, body forces. So we have actually in this nonlinear analysis or in this global assessment, it is more, this FGD should be more like a load level. So we have kind of a scaling factor which we are applying to the given load combination. We should be checking whether this, when the structure fails, that this loading level is above this design loading level. But for simplicity, it is still nice to describe it by this simple equation. So we have this equation, FD is smaller than RD. Now, how to calculate this RD, this design strength? So one way would be to have some calculate some mean response, and then have some safety factors by which we divide it. Something like a material safety factor, gamma M, or gamma RD, which would be the uncertainty in our model. So I would like to show two or three. I will concentrate in my talk on three safety formats because they more or less correspond to the safety formats proposed in the FIB model code, which is, let's say, the only available model code now which treats this problem of safety formats for nonlinear analysis in somehow consistent manner. Nowadays, the other codes which are used, they typically don't address this topic at all. They are always strongly focused or strongly oriented towards linear type of design. And I will let's look at those methods in more detail on the next slide. Actually, here I'm showing one more method, but let's go through them. So first one is this partial safety factor method, which is, let's say, a method which is very close to the standard design approach. That means we make a nonlinear analysis and in the nonlinear analysis, we use the material parameters for concrete, for steel, that are already divided by the associated safety factors. So that means for concrete, we divide by the gamma C. For steel, we divide with the gamma S in think about Eurocode. So then we can say that such a nonlinear analysis directly gives us the design strength. But this will provide the design strength only considering the material uncertainty. But we also have to think about the model uncertainty, so we need to introduce another safety factor for that. I will come to the model uncertainty later on. Because, of course, we have to understand that some model uncertainty nowadays is already embedded in the gamma C, for instance, for concrete, or gamma S for steel, in the safety factors for concrete and for steel. But they are very low, and nonlinear analysis typically requires higher safety factor, model uncertainty. Well, then the second approach here, I'm just describing here it for reference, because in Eurocode, in the Eurocode for bridges, there is already nowadays some safety format which suggests to make kind of an average, to estimate the average strength by using modified material properties for concrete and for steel, which somehow represent uncertainty of these two materials. So that means this kind of virtual mean strength of concrete is obtained by 0.85 times characteristic strength. And for steel, it's 1.1 times characteristic yield strength, which really represents, let's say, mean strength for steel. But for concrete, we have mean strength somehow reduced to take into account for the fact that concrete has much higher uncertainty than steel. And then this gives us some global safety factor 1.27. So this approach can be also used. And then the second approach, which is the third one, which is already starting to introduce some probabilistic assumptions in a more consistent way. That is the Ekov method, which was proposed by Vladimir Chervenka in 2008. And this with this method, you need to make two analyses, one using material parameters and one using mean material parameters, and one using characteristic parameters. So you have two analyses. One, and you can say the one with the mean parameters estimate the mean strength, one with the characteristic parameters estimates characteristic strength. And then we can make an assumption about the distribution, statistical distribution of strength, which is typically log normal. And we can calculate this global factor by this expression, where we can already take into account this beta, which is the reliability index based on the codes. So based for different design levels, it's possible to consider different reliability which is required. And of course, the fourth method is the most, let's say, accurate one, is to make a full probabilistic. So, this, let's look a little bit more closely. What does it mean in terms of probabilistic? So, if you think about design resistance, and if you think about the probabilistic distribution, then if we make a full probabilistic analysis, then we really calculate the distribution of the strength of our structure, and we can really consider the required probabilities for failure, and we can really make a good estimate of the RD, design strength of our structure. In terms of Ekov, we calculate or estimate, we have to understand it is an estimate. We estimate the mean value using the mean parameters. We estimate the characteristic value by making analysis with the characteristic parameters. And we know we can also have to make an assumptions of the shape of our distribution. And we know in most cases in reinforced concrete analysis, it is a log normal distribution. So with this estimate, we can then again make an estimate of the design strength. You have to understand these are estimates, but still quite, let's say, realistic. If we look at this global factor, which will just calculate the mean and then use some global factor, we can understand that in this case, we don't know anything about the shape and of our strength, and it's really just an estimate or a lot of assumptions in this gamma R. And the partial safety factor, if you think about how this looks like, you can see in this case, we are directly calculating this RD. So we have no idea about the shape, say, coefficient of variation of strength. So this method is, let's say, the most simple one, but let's say the most crude one. So this was the method. Sorry, there are some noises. Please turn off the microphone. Okay. So let's describe a little bit in more detail this estimate, this Eckhoff method, which I told you requires two analyses. One with mean parameters and one with characteristic parameters. So in this way, we can obtain some kind of idea about the randomness of the strength of the distribution of the structural strength. And with that, we can then make a quite reliable estimate of the design strength. That means from these two analyses, Rm, K, with the assumptions of the log normal distribution, the assumptions of the reliability index, and the sensitivity factor R, we can calculate easily this global safety factor, which is then used to divide the mean strength obtained by the mean analysis. Of course, we should not forget that this equation only considers the material nonlinearity, but we need also to address the issue of model uncertainty. So let's skip this. And I want to come to this slide where we just compare how these methods work for various problems. So in the past, we have analyzed various structural problems, which is like the beam, where it's a simple structure, beam and bending, and then more complicated failure modes with shear, this also fiber reinforced concrete, also stability problems like this pier. And now this shows the results of these, let's say, 9 problems. And the results here this is basically a table showing the strength, the design strength of these structure elements. It's like a global strength of these structural elements. And now they are normalized. Yes, so to be able to compare it easily, they are normalized with respect to this PSF method, the partial factor method. One where we use material parameters divided by the safety factors, partial safety factors. So you can see what can be learned. First of all, in most cases, especially these simple cases where we really that we can really check easily by analytical solutions, like the bending and simpler shear problems like the first 3, we see there is a very little difference between the individual methods. We start to see a little bit more difference for some more advanced, for some more, let's say, deeper shear beams, which is, for instance, this case 3, where we can see that the probabilistic and Eckhoff methods, they give higher strength. And this, of course, can be by the fact that they are the probabilistic analysis, you can see, is a more advanced type of analysis, so provides more accurate results. So, overall, I think we can see that these methods, they give quite consistent results. The simple methods give mostly more conservative results. Once we have more advanced method, they give a little bit less conservative results. Of course, at the cost of more effort. Now, I would like to show the next part to talk about the model uncertainty. Yes. So that is this this factor. Yes, we have to always understand that we have to understand that we are doing simulation with material models, with nonlinear material models. So there is a lot of uncertainty involved. So it is necessary, therefore, to always validate our models, software, but it can be also validation of a special material model. And how to do that? The best way, of course, is to use some experimental results. So I will show now data which were actually published in one of our papers, recent papers on this topic, published in the FIB journal. And so one example is these. One examples are these reinforced beams without shear reinforcement or with slightly with some shear reinforcement, which is let's say the minimum level of reinforcement. This shows the experiment of the one with reinforcement, one without reinforcement, shear reinforcement, I mean. Typical crack pattern from the finite elements from experiment and only finite element analysis. This shows also the idea when because we also applied all these various methods, but also the full probabilistic method, which then means that we have to perform not a single analysis, but many analyses. For that, we are using stratified sampling methods like this LHS, because those of you who did some probabilistic analysis probably know that if we use the Monte Carlo method, the typical method for probabilistic assessment, we need to make thousands of analyses or 100,000 of analyses, which is of course not possible with nonlinear modeling. So we have to limit ourselves, and for that these stratified methods are a good tool because they enable us to make good predictions with as low as 30 analyses. And this now on this example of this shear beam without reinforcement, we can also see how these various methods compare to each other. So here you see what would be the various results. So the first point is this PSF method. Then we have this Eurocode method and ECOF method. They are very close to each other. This ECOF method, which gives 230, is of course calculated by these assessment or estimates of the characteristic analysis and mean analysis. The experiment is this green point. So we have to understand that the experiment may not be the mean. Of course, nobody knows. And it is also interesting to show here what is the Eurocode formula for shear strength and ACI. So this particular case of this unreinforced beam, it is well known that these formulas are very unsafe side. Of course, in the ACI now they introduce a new formula to take into account in a better way the size effect. So then this is the old formula before the size effect was properly considered. So on this example, it is actually not yet part. We also use it with this uncertainty model, uncertainty safety factor evaluation, but this also shows how this example behaves with these safety formats. So when we evaluate the safety format, we have to analyze many tests, and it is usually compared the test result with respect to the simulation through this theta factor, which is a little bit strange factor because it is smaller than 1 if the simulation is overestimating the test, and it is larger than 1 if the simulation is on the safe side. And then we can evaluate statistically the safety factor, again using a very similar formulas like the ones in the Eckhoff method. So this is how we have to, or we should always perform uncertainty quantification of our numerical model. We did that for ATENA, and we used this case study of 33 cases with punching, shear tests, shear strength on beams, and also some bending beams in bending. So quite a lot of examples covering the brittle failure modes in concrete, ductile, in steel, with and without shear reinforcement, normal strength and high strength concrete, and sizes were from small 0.1 to 4 meters. So this shows just some of these tests that we used, these very nice punching tests by Muttoni and Algren. Here's just for show some video, yes. Some videos also from an animation from our analysis. So this shows the video from this punching analysis. Here you see some comparison of some of these curves for two of the beams, two of the slabs. I'm sorry, these are slabs, punching slabs. Summary of these results for several beams. As you can see, in some cases, it is not so great, yes? And here I again want to express important in this uncertainty study or quantification of the modeling uncertainty is that we need to have a specific or given rule how from parameters that we know, because in each experiment you know something. Sometimes they measure compressive strength, sometimes they even measure tensile strength, sometimes even fracture energy. So these parameters we have to use to always consistently generate all the materials necessary for our analysis, because typically we know only compressive strength, but in finite element analysis, nonlinear finite element analysis, we need much more parameters. Our models, they have, this is ATENA model has about 10 material parameters. So in order that this study is meaningful, we need to have a given rule how from the compressive strength to derive all the parameters and use that rule throughout our study. Of course, if we know tensile strength from the experiment, then we can always update our information. That means we generate the material parameters from the compressive strength. And if we know some parameter in more detail, then we always adjust it. But if we don't know it, these default values should be used. So that's why in some cases the prediction is better, in some cases it is not so good. This is the large beam from Toronto. Again, just to an idea about the numerical simulation. So animation of ATENA analysis. This time it was a two-dimensional analysis because it is a 2D problem. So there were two beams, and here are another beams from this time. Oh no, this is still, I'm sorry, this is still the Toronto beam, but the beam was, there was one beam, but it was first tested, it first failed on the right side where there was no reinforcement, and then it's some ties to strengthen it, and then they continued with the test to break it also on the other side. So then we have these bending examples. some of them failed also by concrete crushing. Here are some results from such analysis, and I go quickly to the end. And this summarizes the results. So from all these tests, we could treat them separately to calculate the safety factor, partial safety factor for model uncertainty, punching, shear, bending. And if we, let's say, take all these together, it would be 1.16. So in this way, we could consistently make some assessment of this model uncertainty, which of course then should be taken into account when making this global assessment. So let me now show how this works on some practical example. I don't know if there are any questions to this at this point. I see no questions in the chat. So what I want to say about this punching, or about this, I'm sorry, not punching, but the safety factors for model uncertainty is that then we can use them specifically if need be. If we know that our structure is really a bending, failing in bending, that means mainly by reinforcement yielding, we can apply uncertainty factor 1.01. If we know that it is really a punching problem, we have to apply 1.16. Let's say if we don't know, if it is, sometimes it may be difficult to really recognize in our structure what is the failure mode, then we should use, of course, the most conservative value, that means 1.16. So let's have a look at now at some practical applications. So for that, I will open another presentation. There is one question, whether JCCC has other recommendation for SF. SF, I'm not sure what do you mean by SF, by the safety factor, I guess. I'm not sure. But JCC is really a probabilistic code. And I think they provide guidance for this probabilistic, for the fully probabilistic assessment. And I don't think they treat the model uncertainty. They provide maybe just general framework, how this model uncertainty could be evaluated by probabilistic approaches, which is basically what we have done in this study. Uncertainties on the load path, there is a question. What is the effect of uncertainties on the load path? Well, this is, of course, very important. This is, of course, very important question. And let's, maybe I will address it in my next presentation. So the next presentation, I would like to show some examples how this can be applied on some practical situation. So I will use a relatively simple case, which we were actually working on recently in one of our consulting projects. So the idea or the problem there was this kind of slab. This is a slab which is supported by continuous beams. And we are focusing on this because it's a big structure. Of course, we could analyze the whole thing, but we really want to simulate the strength of this continuous beam, which is supporting the slab. And all of the beams are the same, so it is possible to focus only part of the structure. So this is the continuous beam I'm talking about. So we are modeling half of the beam. The reason we model not just one beam or two spans is because of the loading. Yes, some of the loads should not be distributed uniformly, and there should be load combinations are different, so we should always address these different load combinations. Because of that, we are modeling half of this beam, and also always half of the slabs. So this is the model that we developed in ATENA. This shows the boundary conditions that we are using in order to properly capture the simulation, this axis of symmetry conditions. We have to apply the symmetry conditions. That means we have to so these are shown by these green lines indicating fixed support in Y condition, blue line support in X condition. And to simplify our model, we are using also the fixed contact approach in ATENA, where we can have uncompatible meshes. This shows these fixed contacts between the beam and the supporting columns. And now the important part of any nonlinear analysis is always to define the loading history, which goes back to this question about how the loading history affects our analysis. So this is, of course, an important question, and we should understand that every time we perform such a nonlinear analysis, we should perform some sensitivity studies. Some of these sensitivity studies can be done only once, like I presented before. Those are mainly the validation or sensitivity studies to validate the model, to find out how accurate is the model, to determine this model uncertainty factor, which I shown before. But then there should be always sensitivity studies which are project related. So we should investigate the step size, how large part of the model we should analyze, what would be the effect of boundary conditions, effect of mesh sizes, and so on. So this always should be done as a part of each project. On the other hand, regarding this loading path, or loading scenario, we should study that, but on the other hand, there are certain things which are, let's say, clear from how the project was built. Yes, first there was a dead load, then there was a live load, then maybe there will be some overloading. So this is exactly what I was now getting into, is that we need now to define some loading history that we will use to check our structure. So in this situation, in particular situation, we had one interval representing the dead load, which is quite clear. One interval representing live load. Then one interval representing I'm sorry, the second interval was representing the permanent load. Yes. Structure of the floor. And then we have the live load. The live load, of course, can have different positions of the live load depending on the load combination. So this, for instance, shows one of the combinations, which in the end showed to be the critical one. But in practical situations, we have to estimate maybe several of these load combinations. One which would be full, load everywhere, or maybe every second span is loaded. And then we have the safety factors for the loads. That means for permanent loads, it is typically 1.35. For the live load is 1.5. And it is in the loading history, I think it is advantageous to make this separate. That first we apply these loads with factor 1. Then we apply these additional parts of this load to reach the required load combination. And after that, we now want to keep increasing the load to find out the strength of the structure. So what we see in the end is this kind of graph. But in this graph, we have to understand there are various load levels. First, we applied the dead load only. Then we applied the character combination, which is basically one-time dead loads, one-time live loads. So one-time permanent loads would be more accurate, and one-time live loads. Then we apply the difference to reach the design combination, which is difference between 1 and 1.35 for the permanent loads, and difference between 1 and 1.5 for the live loads. And after that, we should keep increasing the overall design combination. That means this one, this whole design combination, which in this case is, let's say, relatively simple. That's why I selected this example. This 1.35 times the permanent loads plus 1 times 5 the live loads until we reach the failure. And then it is possible to make this comparison using the design equation that I mentioned before. In this case, it is relatively simple because we use this approach with the partial factor method. That means our analysis already is using material factors, material parameters divided by the safety factors. So now let's talk also about the evaluation of results. So this, what is most typical, most important is always to look at the deform shape, because this always tells us, so always first and very good estimation whether our model behaves the way it should, and also gives us an idea about the failure mode. So this suggests in this case that there is maybe some shear failure or maybe it is shear failure, or from this it might be even a compressive crushing in the negative moment. Now, these evaluations that I'm talking about now is really specific to ATENA. In ATENA, if we want to look and understand how our structure behaves, I always recommend first to look at the deform shape. From that, we already have an idea. Deform shape at failure, just behind the failure mode, behind the failure road. So that means at the end of this load displacement diagram. Next thing would be to look at the cracks. This picture shows the crack openings. This already indicates me that we have some development of a diagonal crack. And then to look at the reinforcement stresses. And we know in this case, the yield strength, design yield strength was 437. So we see that we have stirrups yielding, we have yielding of the bottom reinforcement, and we also have here yielding of the top reinforcement. So from this, it might say, okay, it's failing here in bending. Maybe here we have a shear failure, and we have a failure in the negative bending moment above the support. But sometimes the stresses don't tell us the whole picture because we may not really know. It's difficult to say which reinforcement is really yielding. So better to support this by looking also at the strains. So if we now look at the strains, we really see that the most critical situation and strain development is in these reinforcement stirrups. And then, so this shows that really we have a failure in reinforcement is yielding. Now we should check also whether we also have a concrete crushing. For that, in ATENA, the best parameter to look at that or to evaluate this situation is to look at the equivalent plastic strain. And this equivalent plastic strain can be then compared with the epsilon CP. Remind you, ATENA users know this parameter. It is the parameter in the material. We open a particular concrete model. And we go to compressive behavior. There is this parameter epsilon CP, which basically says what are the plastic strains when we reach the compressive strength. So every time we see strains, plastic strains higher than this value, that means we are on the softening branch. In reality, we may not see softening because we may have a 3D effect. So there may not be softening, there may be even hardening. But when these strains are larger than this epsilon CP, we understand that the strains or the concrete has reached really the crushing stage, the crushing state. Maybe still due to confinement, the stresses may be still increasing, but the concrete is really crushing at that point. So that's why we are, in this case, the epsilon CP was this value. So anything that is above this value, which is everything in blue, basically indicates a concrete crushing. So this looks like we have if we look at these things together, that we see this stirrups yielding, we see the development of this diagonal crack, and we see the fact that we have a crushing here. So we really, from that, we can derive that the main failure mode is the crushing of the diagonal strut due to shear failure. So this is one example, and I wanted to show another one which is more complex. This is this bridge, but we are running out of time. I think I should look at some of the questions here. So let me look at the chat window. So there was a question from Hassini. Are these simulations capable of simulating the delamination crack of the shear crack? There are flexure cracks at the root of the shear crack. Well, I am not fully sure where this question is aiming at. But yes, the delamination can be captured with these simulations. Actually, in this problem, in this slab, which is not shown here in this case, but in some of the situations, there was a delamination simulated. This it's maybe difficult to see here, but in this particular situation, this slab was built separately as the beams. It's actually prefabricated, partly prefabricated structure. So there was a weak interface between the beam and the slab. in some of the models that we did in these projects, this interface was also simulated and the delamination was observed.
Okay, but to be honest, the question was for the previous presentation where you showed this shear crack, the critical shear crack. Sorry about that because.
You mean the previous presentation?
Yeah, the critical shear crack you shown with the delamination crack.
Okay, go back to the previous presentation.
सर ये कैलकुलेशन है मटेरियल मंगवा दो तो वो बोलता तू कह रहे तो पड़ा हुआ सर पर देखो पे
You mean this one? I'm sorry, somebody please turn off the microphone. Somebody is speaking there. Can you ask the question? What was it about?
As I remember, yeah. Can you go down a little bit? Yeah, that one, the previous one. Slide 34. Yeah. In this one.
Maybe you mean this bottom part, no? That
yeah.
You see kind of a bond failure.
Yeah, I need to know whether, like, how was the critical crack identified? Like, weren't there any flexure cracks at the root of the? Yeah.
Sure. It started first as flexure cracks.
Okay.
Actually, this was this first drop. This first drop happens that a big flexure crack propagates in the middle.
Okay.
And later on, these flexure cracks open. They spread first to the supports, and at some point, yeah, you can see that in this animation. Yes. Yes. Let me show. Okay. So see. Yes. So first, it starts as flexure cracks. These cracks are spreading. You always also nicely see that at the bottom there is reinforcement. Yes. So quite heavy reinforcement. So we have a lot of fine cracks around the reinforcement, and these fine cracks always at some point coalesce into a one major bending crack propagating through the height of the beam. And as you see, as the cracks propagate towards the support, they start to propagate as shear cracks. And one of these shear cracks then becomes dominant, causing the failure mode. And indeed, there is also kind of a separation. You can say this is like a bond failure, basically the bonding of the reinforcement. So this is another interesting feature, is that this ATENA model, or not only ATENA model, but any good nonlinear model, when you have a sufficiently fine mesh, it actually can capture even the reinforcement bond failure.
Yeah,
because the reinforcement bond failure is usually a cracking failure by the surrounding concrete.
Yeah, because some other finite element analyses are not capable of capturing that delamination crack. That's why I asked the question. Thank you.
Okay. Yes, with ATENA we can do that, but as I said, you need a relatively fine mesh to be able to capture that. Okay, there are other questions. Vasilis, are the column supports modeled with elastic steel materials almost rigid? Yes, in this practical example, the columns were added there just to have some support. So they were not modeled by steel material because they were from concrete. So, but they were modeled as elastic material. Is this model already available in ATENA installed examples? Not, it is not. It will not be. If there is interest, we can, I think, provide you with this model. It's, I think, secret. Kashi, thanks for such a wonderful presentation. If I can elaborate a bit on the equivalent plastic strain, how to estimate that? Well, I thought it is quite clear. This is one of the input parameters in ATENA, and it can be easily generated from the known softening curve of concrete in compression. Or not softening, I mean stress strain curve, working diagram. If you make a loading test of concrete in compression, then you can easily determine the strain at the peak. And if you subtract elastic strain at the peak, you get this epsilon CP. This is one of the input parameters in ATENA. I again emphasize that it is only the plastic part of the strain at the peak, yes, not the whole strain. But you can easily calculate that, and it has a clear physical meaning. In ATENA, we try to be sure that all our parameters have a clear physical meaning so that engineers, even if they don't know them, they can at least make some estimate or have some kind of engineering understanding to be able to make a qualified estimate if they don't. Karel Samets is asking, can you simulate slipping failure due to rebar separating from the concrete matrix? Yes, I think I answered that already. In ATENA, of course, if you have, as I said, if you have a sufficiently fine mesh, the slipping failure of typical ripped rebar is basically a cracking of concrete. So you can simulate that in ATENA. In addition, in ATENA, we also have a bond model that even introduces slip law. You can simulate this, even this slipping effect. Another question. There is a question from Rad that some engineers may be afraid. Yes, I think this may be the case sometimes. But I am not saying that we should abandon the classical ways of checking, but or design or using analytical formulas. But I think all these methods should work together. Sometimes you have cases when the analytical formulas, let's say, are questionable to apply. So then nonlinear analysis is a good tool to make a more qualified assessment. Another nice thing about nonlinear analysis, or even these global nonlinear analysis, is that they sometimes help engineers to discover fail modes that they had not considered. So it is a very good checking tool and a supplement to classical design methods. Mikhail is asking, when running an analysis for global safety assessment, I understood that you also increased the dead load up to fail. The dead load was increased together with the live load. Is this realistic? Can it interfere with the failure mode? Yeah, of course, this is a question, yes, but if we think about the way the codes work, is that we have some linear combination of loads that we are supposed to check. So I think it is quite natural to really make this consistently that all the loads should be increased to fail. This then I think also a conservative assumption. Of course, it's a question whether the dead load can increase so much, but on the other hand, that's why we have this. That's the same reasoning why we have 1.35 for the permanent. Yes. All right. I think there are no more questions. And also we are running out of the time, a little bit over the 1 hour that we promised. So I will stop the recording also.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.